It's just another night, and I'm staring at the moon.
This is Vicky, and today I'll be talking about part 1A of Lab E2. So now we assume VF is equals to 2 volts, whereas ID is equals to 10 milliamp. And from the schematic diagram, we can see that the VDD is connected across the diode and then RL, and then connected to the collector pinot of the NPN transistor, whereas the port connected to the RB and then to the base pinot, and whereas the emitter pinot is connected straight to the ground. So here we assume that VBE is equals to 0.6 volts according to the datasheet, and VOH is VDD minus 0.5, so the VOH is equals to 2.8 volts. So now we want to find what is the value for RL. By using the formula, we can see that RL is equals to 130 ohms, whereas RB is equals to 4.4 kilo ohms. And the HFE is also given 200 from the datasheet, and then IB by using the formula 10 IC divided by the HFE is equals to 5 times 10 to the power of negative 4 ampere. So this is the schematic. So now moving on to the circuit board. So the coding used to run this circuit is based on the last part of Lab E1. Moving on to the code, as you can see here, this is the code used to run this circuit. Okay, so moving back to the circuit, we can see that the LED is blinking slowly. That's all. Thank you. Hello, my name is Vicky Ngui. Today I'll be continuing on the second part of part 1, where we will be using a PNP instead of a NPN. So the difference between these two is just that the PNP will be placed closer to VDD, and the diode and the load resistor under here. So we will be using the same assumption of VF equals to 2 volts and ID equals to 10 milliampere. So our VOL will be 0.5 according to the data sheet, and since our VC is connected to the diode and the load resistor to the ground, it's assumed to be 0 volts. So moving on, we will have our load resistor where is calculated to be 130 ohms, where our RB is equals to 1636.4 ohms. So moving back here, based on the datasheet, we have our HFE equals to 90 based on the datasheet, with our IB equals to 1.1 times 10 to the power of negative 3 ampere, and our VBE according to the datasheet of 1 volt. So we will be using the same coding as we did using the Lab E1 for our NPM. So as we can see here in our circuit, this one is following the schematic design of this one. Is actually similar to part 1 of part 1. So from here, I'd like to end. Thank you.
Hello, I'm Melvin. I'll be demonstrating part B of the Lab 2. Firstly, I will show you guys how I write the code. I have chosen 3 ports from the MCU, which is the port C2, port A2, and port A12. Basically, port C2 is function as a data, and port A2 is as a display, and port A12 as the clock. And I named them as SER, RCLK, and SRCLK respectively. And here I have a initial binary display function which I use to enable the port and enable the clock. And this is the binary display that I'm going to show you later, how it's display the code from 000 to 1111, and this is the function for delay. And here is how I write the for loop to let it go for 64 turns in order to bring from 000 to 1111. here he comes call for the function of the binary display, and this is how I enable the clock, and this is how I enable the port for port C and A, and set them to a high drive strength, and I set all of them as the output. And here is the display that I put a for loop and let it go for four rounds because there are 4 binary number at once, and I set for the clock so that it can check and let it move for one number so that it can add one by one, and later it will print the output and clear the output to make it blink. And here's the delay functions, which is it delays for around half a second. Now I would like to show you guys how the real thing functions. But firstly, this is the schematic diagram. Okay, firstly it will start from 0, 0, 0 to 0 to 0, 1, 1, 1, 1. And it increase bit by bit until it reach 1, 1, 1, 1. And it will start again from 0, 0, 0. And this thing will only stop when you turn it off. And I think that's all for me. Thank you.
So open your eyes